Okay, so separating modeling and simulation aspects in framework-based modeling and hardware-software systems. So, what's this presentation about? Why such a long title? Well, I guess if I quote Gary Flake, it's going to be a little bit about toy problems and fudging results, but it's definitely about simulation. So, instead of trying to explain what the subject is, what I'm going to talk about, I'm going to present the why of the work. So what's the problem we're trying to solve? What's the context? So as in the software industry, which is going through a crisis, can't deliver good quality software on time, on budget, with the right functionalities, the hardware domain is going through something similar, which we call design productivity crisis. And what's the problem? Well, there's a productivity gap between the amount of transistors that is growing exponentially, how much stuff we can put on silicon, compared to what a designer could actually effectively design and create in an intelligent way. I need to point out, though, that this is a logarithmic scale, so it is growing exponentially here. So, one more time. Sorry. So Moore's law does work, but our brains can't keep up with it, though. So the context of the work also, most people are looking towards EDA tools, electronic design automation tools, to help with this productivity gap. So we're talking about a $6 billion industry, but this is just the tools. I found a nice little article talking about a $300 or $400 billion industry for the hardware sales. So this is the context in which we're working. So what I'm going to talk about today, talk about some current solutions or some past solutions to try to help with this productivity gap. Present some vocabulary, because this is a software symposium, so try and get in some hardware vocabulary in. Current approaches, ESYS.NET, and where exactly do we fit into this presentation with .NET technologies. Separation of concerns, SOC-ML, so System on a Chip ML. And conclusions. So once upon a time, people used languages like VHDL and Verilog to describe systems. So instead of having hardware people deciding on designs, placing transistors on silicon, basically we started to describe systems with languages that resemble programming languages, such as VHDL and Verilog. So these languages were used to describe electronic circuitry and permit the simulation. So the toy problem or the fudging results comes in here. And VHDL was designed by the DoD, standardized a couple of times in the history. So what kind of semantics does a language of this kind have? Well, if I bring this to a concrete example, we have a chip here. We often talk about the concepts of a module. So a module would be equivalent to a chip. A port would be equivalent to a pin on the chip. And the signal would be equivalent to a path on the board. So I'm just presenting these semantic notions just to get the vocabulary in, so everybody here will understand what we're doing with the language and how .NET fits into this. So just to go inside a module, modules are hierarchical, like silicon is, like chip design is. Modules can contain submodules. But a module contains processes which do computational work. So a process could be seen a little bit like a function, but the difference is that they all run in parallel. So basically, the best analogy would be threads. Okay, silicon, all the elements of computation in silicon all run in parallel. So a chip takes inputs, all the silicon processes in parallel, distributes the values in the silicon, brings them to different submodules, etc. So here we have an inner signal, which connects to a port with an outer signal. So we used to design hardware systems, but just hardware systems is not the reality anymore. I mean, just with these smartphone devices, systems are much more complex than they used to be. I mean, we don't just have hardware stuff. We have software stuff. And in the future, and even today, on the drawing boards, even some of the research laboratories, we have what we call system on chips. So we have micromechanical devices embedded into the silicon. We have optical networks, multiprocessors on those optical networks within silicon itself also. So within a chip, I mean, you have a whole complete software, hardware, micromechanical system. So this productivity gap is just exploding. So the present and the future. So what people have been doing, or what they've been trying to do to solve this problem, is create system description languages, such as System C, System Verilog, and Spec C. So the purpose is instead of having a language like VHDL that permits to describe systems that hardware systems, more at the register level or signal levels. We're talking about stuff that can represent hardware and software, because like the PDA, they're both, and offers higher level of higher abstraction levels when modeling to become more productive, and also better systems that permit the creation of test benches to test these systems in a much better way. Because also, we have to put this in context. I mean, like a PDA phone, the time to market we're talking about is like 18 months. So besides the fact that we have to do something smart, intelligent, marketable, we have the whole time frame from paper to product is 18 months. So we have to make sure that we test effectively what we're putting out, because once we burn that silicone chip, it's millions and millions and millions of dollars lost if it's not correct. Software, you can just update it. And also to gain simulation speeds. Since systems are becoming more and more complex, we want to simulate them before we produce them. But since they're so complex, it takes so much time to simulate them, sometimes we just can't do it. So we're kind of guessing a bit. So System C, I'll talk about System C because all of our work spins off of System C and goes up in the future, and also will help me place this presentation within the context of this symposium. System C is a library framework in C++, which was announced in 1999, which permitted the modeling and simulation of hardware software systems. It offered much higher abstraction levels that were curiously available in languages like VHDL, like the concept of channels. So instead of modeling with the concept of a signal, you would connect modules with channels, which could abstract crossbars, very complex networks on chips. Okay. The vision that the hardware industry has of systems now is equivalent almost to real-life networks. Just replace every one of the computers here in this room by a processor, and all of the wiring by the networks on the chip, and that's basically what you get, but in silicone. And also much higher levels of abstraction for communication and interfaces. So almost going to contract-based level communication with different chip modules instead of having like bits and pins and stuff like that going around. So, and also System C added concepts of threading and verification for better modeling of software. So drawbacks of System C. Well, since it was based on C++, there's no concept of reflection within the language. Well, besides RTTI, but I mean, that's fairly poor of a system, never was standardized correctly. So there's not much to do with that. Also, the fact that when you compile down the models that are created with the library, all the constructions, all the hierarchy that you've modeled gets broken down completely, because the compiler will optimize everything away. And also, that system in particular lacked very poor expansion points within the simulator. So you had a whole big community of people trying to add on tools onto the simulator to, again, help with productivity, verification, stuff like that. But every time you would move from one tool to another, since your model and your simulator are hooked in together, you always were recompiling your systems. And so people were trying to add in, hacking their way into the system. So this was also a problem to try and graph third-party tools. And also C++ is fairly complex, especially coming from a hardware domain where people don't have very little knowledge of object-oriented programming. I mean, when they code in C, they see the assembler, the binary passing by. For them, objects does not make any sense. So there was some problems with C++. So, which brings us to ESYS.NET. So what we did is, by looking at this system which was available, And by looking to C#, which was becoming available also on the industry, we decided, hey, I think we can do better than this. So our team basically took System C, brought it into C# to try and gain the elegance of the language and the simplicity of the language, and also to gain reflective capabilities, garbage collection, and also the use of attribute programming to bring some of the modeling concepts closer to declarative than to imperative styles of writing. So this is an example of an eSys.NET model. So to be able to create a concept of a module, as I discussed before, just by deriving from a class, it's almost like if you were tagging your code here, saying this one, I wanted it to be a module. So forget the notions of object-oriented. To derive almost becomes a tagging mechanism. The use of attribute programming to say, this function should become a process. So all the functions that are tagged have a semantic that they should be running in parallel. Also the concept of ports here. So we have a Boolean import, a clock input port, etc. So there's enough semantics in these systems to be able to model hardware-software systems. Our laboratory created a number of tools because of the reflection capabilities of the environment and the infrastructure for sophisticated verification based on LTL expressions. Certain tools that the System C community had not yet come out even after 5 years of development because of all the complexity of developing around C++. Within 4 months, we had a tool out. So our aim was also to bring the .NET technologies to help us create a cleaner environment, but also an easier way to develop tools around it for this EDA industry. So, current trends. People at the moment, so that's what we're doing. What are people doing besides us? Well, people are attacking the problem from different angles, the productivity problem. Creating dedicated languages with higher levels of abstraction, such as System Verilog. Either doing library framework-based solutions, such as System CNS. I've also seen, for the Ruby fans, a hardware modeling based on Ruby, called Ruby HL. Others are using sophisticated EDA tools using proprietary technologies, working visually. But I guess to come back to Gary Flake's presentation again with the long tail concept, the framework-based solutions are emerging as being the status, are becoming more and more prominent within the industry because they're free to build, they're easy to extend, whereas these tools here are it's hard to work with them and to bind yourself within the environments because they're proprietary solutions. And creating dedicated modeling languages, I mean, not everybody's an expert in language theory, so it becomes very complicated. And also to create tools around these kinds of solutions become very complex also. So the problem now, why are we still working? Why hasn't framework-based solutions taken completely over? Why are we still working on framework-based solutions? Well, basically, there's been very little design work that have been done on these solutions. So even though people believe in framework-based solutions, nobody has spent a great deal of time actually designing them correctly, because we always have to put this back in context. The hardware community are not software necessarily engineers, so they're looking for a solution which fits the problem, to simulate faster, to model, but everything that's developed productivity tools around and stuff like that, they're not very interested, or it's a second thought. So that's where we come in. So basically, I'm going to talk about separation of concerns and our work. Basically, at the moment, what we see in the framework-based solutions, and I'll change my vocabulary at the moment, which will help with the presentation. I'll replace framework-based solutions with a DSL. Okay, so like Martin Fowler talked once about internal DSLs versus external DSLs. So framework-based solutions in this concept is an internal DSL. I'll come back to this afterwards. Okay, so at the moment, what we're seeing is that we're seeing simulation and modeling semantics. They're intertwined, and when people create their models, whether hardware or software, in our framework-based environments, the models are connected to both. This is kind of odd, though, because it's almost as if you were programming for a specific compiler. I mean, usually you don't want to do that. You're writing with the semantics of the language, and you're trying to avoid using pragmas for a specific compiler if possible. Okay, but at the moment, this is not what people are doing. So you get into this problem, like I was discussing before. I have a model. I model using a specific framework. I compile it. I can run it against an implementation of that framework. I use the tools. Oh, this guy created this other tool, but for this other hacked implementation, oh boy, this doesn't work anymore. I have to recompile my code. But oh, if I bought this third-party block IP, but I don't have the source code, so I'm kind of screwed. So what do I do? So we're seeing all this amount of problems showing up. So basically what we want is this. I mean, this would be clean. So internal domain-specific languages. So basically, framework-based solutions, SDLs, are internal domain-specific languages. And the problem is that people are not viewing them that way from the hardware community. So we have that view, so we're trying to push the design of these DSLs in a cleaner fashion to have better model reuse and better separations of concerns. So basically, what tools are we using to design better DSLs? And also, at the moment, the techniques that we're using would probably be different if we were using Ruby. Because since we are in a statically typed environment compared to a dynamically typed environment, we're constrained by some of the syntactical elements and by the type system, which when you're developing in Ruby, you can kind of get around certain things with some methods that are not implemented, and it's kind of odd stuff that you can do. So these are the tools that we're using, better design patterns in modern languages. So basically, the mass of our work is made possible because of basically these couple of lines of code. We waited 2 years until the 2005 version came out to be able to have dynamic binding of generics. Because the gyro project was available on the rotor system, but didn't support dynamic binding. Anyways, this is a very powerful feature that we use. So our starting point to create a better design, a better DSL, in a statically typed environment, language, host, was to take esys.net and analyze trying to find a boundary. Now, just to help people understand the context of the design of the simulation aspects and the modeling aspects and all that, most framework-based environments, such as esys.net, are basically what we call event-driven simulators. So basically what you have is you have a queue with events which have timestamps, and on those events are hooked up threads, basically the processes that have to be executed at those timestamps. So the engines basically go through the queue for the current timestamp, takes out the event, executes all the threads. Whatever those executing threads could actually make other threads become active, and will go like this. When it's finished one element in time, it goes to the next element in time and execute like this. So it's a traditional event-based simulation. So why am I talking about this? Well, basically, since the core of the simulation is based on this, and we have modeling aspects such as processes, events, there's a relationship between those. One has to know the other to be able to integrate within the simulation environment. So basically, some of the problems that we had finding that boundary was in the modeling concepts that we have in the modeling languages, we have a concept of event that's going to be used by the modeler to create the concept of an event. So instead of having a signal wake up, send a bit, that a process is waiting for that bit, and when I get the right 0 or 1, I'm going to start executing as in a handshake. Well, I'm going to have the concept of an event. So when one process starts up that event, the other person knows. So we're abstracting complex communication schemas. And also within the processes, the functions I showed before, which is our processes, there's semantics of weight. Since we're modeling hardware, we have to model time. So we have to add elements of time. Anyways, these two elements were intrinsically hooked up within the simulator. So we have to try and find a way of trying to get them out, trying to separate a true separation of concerns between the modeling and the simulation aspects with these two elements. So what did we do? Well, we said, well, if we create a DSL, which only uses interfaces, well, there's no implementation, so there's no way of getting all mixed up. And whatever we can't put as interfaces, well, we'll use virtual methods with no implementation, so they can't be executed. So once we have that, well, we know we're completely separated from an implementation. So now we'll have other problems. How do we reconstruct the implementation after we made those choices? So the modeling environment is basically a whole bunch of interfaces. Besides here where we have virtual methods with no implementation. Okay. So this is basically an example using the new environment. Okay. Which is interesting to note is that we don't instantiate any of the objects here. They don't add any information to the model. I mean, in C++, this would just allocate on the stack instead of doing the new, which would allocate on the heap. Okay. And also, some of these things are interfaces, so we can't instantiate them anyways. Okay. So the question is that once we have a model like this, how can we reconstruct something that's executable for simulation purposes? So basically, for the instantiation problem, there's the factory design pattern. We basically got rid of that idea because you have to know too much you have to know the concept that the factory is there. So this is implementation details, not modeling details. So we look towards inversion of control. So I'll skip. Well, inversion of control is that you let the environment decide of an implementation for a service that you need. Traditional ways of implementing inversion of control were not good either for us because they were they were not transparent enough. So we use basically reflection techniques. And the techniques that we're using, because of the generics and the attribute programming, we could not have done in Java. Okay, neither C++. So this is why we're using the .NET platform, because we don't know of any other environment which is statically typed, which we could do this with. So anyway, so we're basically using reflection to go through a module, scanning the fields. If they're tagged with their certain subclass relationships and superclass relationships, we basically instantiate the right implementation, set it up on the field instances. So, and also for the virtual method problems, but basically what we use as a solution was using proxies. So basically what we do is that you wanted this class, we create a proxy on top of it, which implements the methods for you. And what's being executed is that when the environment's calling your functions, what's calling actually the proxy functions. So we're basically using distributed technologies, proxying, to solve the virtual method problems. So for this case, we created a proxy. I'm going to skip this. Basically, we're using a library called Dynamic Proxies from the Castle project, which is open source. So the benefits of the environment is that we have perfect separation of concerns. And also, since we're using proxying and stuff like that, it's easy to hook up verification tools to intercept. It becomes possible to transparently have a model which was compiled and move it from one simulator to another, which becomes very important. I'm going to skip through some of these slides for lack of time. But what becomes important for us from a simulation point of view is that imagine now, at the present, people are using software simulators to simulate these models, such as System C. But since our models are completely separated from the simulator, we can imagine a system that through reflection actually uses hardware emulation, configures FPGA technology, so reconfigurable technology, to simulate parts of it, which is completely transparent to the designer, which he just created his model. Also as simulation technologies and dynamic code emission becomes more and more mature, and understood, we can imagine that somebody had a model. He's using a new generation of simulators, which generates the complete simulation in a certain fashion where he gets tremendous speed-ups, many orders of magnitude. So that person that created this model 10 years ago, 5 years ago, can gain that advantage without having to rewrite anything. So basically what we're creating is this stack, our true separations of concerns for modeling, simulation concerns on the top. We're creating a modeling framework. We're using a simulation framework which uses the semantics of that modeling framework. So by creating a model based on the modeling framework and by instantiating an implementation based on the simulation framework, we basically get an implementation of this. I'll skip over this. So if I try and bring this back in the concept of this presentation, so there's a lot of talk about DSLs, especially when Ruby comes around because of its elegant syntax. I've seen people create DSLs almost like natural languages. They basically string up methods that are basically words and verbs, and some of the words and the verbs that they don't want an implementation for is just like an empty method, and the rest of the methods they have an implementation, so they get an executable DSL, which is natural English. The problem is that the implementation is also within the semantics of the DSL. Shouldn't we be separating the implementation from the semantics itself? So we're also exploring in that kind of context what are the advantages and disadvantages of doing it, but it's just a cleaner design, permits you to have a model that you can move around. So your program can actually move from implementation to implementation, which can be done with actual inner DSLs. So the future work that we're working on is to redesign ESYS to go further, separating verification semantics also, because that's it. Hardware people just like dump everything in the same melting pot. Modeling, verification, simulation, whatever they want. So we're trying to create clean boundaries for easier tool development, interoperability between tools. Any questions? Thank you.